received his Ph.D. in experimental physics and material science jointly from Vilnius University, Lithuania, and Lyon-I University, France. His current interests are in the field of light-matter interactions occurring in small space at the nanoscale and time, femtoseconds. He planned, established, and directs a multi-user nanotechnology facility at Swinburne, open to the Australian National Fabrication Facility users from December 2011. His research is focused on applying principles of light field enhancement and its spectral control for applications in micro-optics, solid-state lighting, and solar energy conversion. Professor Juodkazis has contributed to the development of a three-dimensional laser printing with nano/microscale precision using femtosecond laser for applications in opto-fluidic, micro-optics, optical memory, and photonic crystals. He has shown experimentally the creation of high-pressure density phases of materials using tightly focused ultra-short laser pulses. He demonstrated that nano-textured surface of SI, so black silicon, has bactericidal/biocidal property and acts as mechanical antibiotic, which can be mass-produced. This work received 2017 Eureka Prize for Scientific Research in Australia. He is a fellow of the Optical Society of America, OSA, and the International Society of Optics and Photonics, SPIE.
Okay, so thank you very much, Daniel. So now let us welcome the speaker to give his keynote talk. Welcome, Professor Saulius.
Okay, thank you very much for introduction. I'm sharing my screen. Is it getting through? Can you see it?
Yes, Professor Saulius.
Sveiki, čia Darius iš lazerinių tyrimų centro. Jo, aš norėjau dėl gardelių specifikacijos, jeigu atsimenu tą klausimą.
Okay, so I can start, right?
Yes.
Yeah, so thank you very much for introduction, for invitation to this meeting. So it's organizing committee VJ, so I'm happy to be here. The conference is cross-section between optics, holography, and material processing machining. So this is second day, and I want to show what can be done with ultra-short femtosecond lasers for modifying materials, and some applications definitely can be very useful for optical domain. So let's start from recent things which are evolving in femtosecond lasers. So this is actually bringing more motivation for industrial applications. And then in the results parts, I want to show some kind of unusual applications which were unusual some years ago, but now they can be driven to a very different scale. It could be really on the large areas and really useful things. So we can write modification by lasers inside the volume of in 3D with the 3D freedom inside volume of transparent materials. We can define surfaces by ablation, make 3D optical elements if we want. Also, we can write large areas, for example, for applications like solar cells shown here. We can make masks for plasma etching or chemical etching. And the very final application, more recent, is we can just use femtosecond laser pulses exactly as we already know for electron beam lithography. We can make nano writing on large areas. So all those applications can be really practical now. So what we can spot in the field of development of ultra-short laser applications, it's evolving over 40 plus years, and we see that very recently, not very recently, but let's say this century, 20 years, we see a new trend. We see that average femtosecond power is increasing every 2 years. So it means over the 20 years, it's 1,000 times. How we know this? It's the conference in Photonic West conference a couple of years back showed the development of femtosecond lasers, and these are simple lasers, tabletop you see in this image. So the energy via repetition rate. So you can have 1 millijoule pulse energy, which is already huge, at 1 megahertz repetition rate, which is defining the point here on the plot, which is 1 kilowatt. So these are lasers can be made by different femtosecond laser techniques. So this is laser physics talk, and they are very optimistic that this can be scaled up even in further, more than 1 kilowatt. If you look what one of the popular laser producers, Amplitude, is showing in their product line, so from 1 watt laser 20 years ago, now you can have similar size laser on your desktop, optical lab, which is 1 kilowatt. So this is exactly how we can calculate this trend that power is doubling every 2 years. If we speak with some other vendors, Lithuanian company Light Conversion was exactly following the same direction. So we have Moore's law for average power, which is basically counting photons in time, is scaling the same way as transistors on the surface area of the microchip. So this is Moore's law, which is really invitation to larger use and applications. And probably this is already driven by applications. Silently, the producers of lasers, they know that they need more power, and this is now available. So be ready to have 1 kilowatt laser ultra short pulses at high repetition rate. So this can be now used for fast removal, large volumes of materials, millimeters cubic per second, and this is already competing with some mechanical machining tools. And obviously, we can fabricate large areas, and I will show this for what we are doing in this area for femtosecond laser machining of surfaces for solar cells. The technique itself is very simple. So you have your laser beam, you tightly focus it on your samples. At the very beginning, it was always with the spirit of polymerization, you need very tight focusing in your resist. But in fact, that tight focusing uses soil immersion way of focusing inside resist, which is less practical. So you can still focus your femtosecond pulses inside transparent material on the surface for ablation or modification. And with the tuning of intensity for modification threshold, you really can localize what you are writing with a very, very high precision, and it can be sub-diffraction limit. So what happens at high intensity in your focal spot, you can drive your transparent material, you can ionize it and create free electrons, which are helping you to absorb more light in a very thin skin layer. And this is energy which is absorbed later driving your modification. So the light is already gone. So light is only sub-picosecond, and this evolution of modifications is happening later. And the most kind of violent and largest modification you can think you can write inside volume of transparent material would be void. So this was our initial interest. So can we modify very strongly material, having very well-defined voids inside transparent bulk volume? So the set of conditions which we can reach with quite simple tabletop lasers, here it's fluence, and because pulses are very short, intensity has very high values here. So we can start with the small pulse energy, small fluence, then we can have simply heating of material, and then we can drive it to melting, evaporation, ionization, and going into plasma. So this is all phase transitions, which you can actually cover with the 3 orders of magnitude, influence, and intensity. So very popular 3D laser writing for polymerization actually is happening somewhere in this range, around 1 terawatt per square centimeter. So it's high intensity, which is already making ionization of materials. So it means you are generating electrons when you are modifying your materials. There is a popular model from early beginning of this field, which is capturing very well ablation threshold of dielectrics and metals, and some other kind of experimental observations are well described by this method, published in the paper here below by Eugene Gamali and his team. And this is a very simple model, which is accounting for impact, avalanche ionization, and multiphoton ionization. These rates are calculated using Drude model. Certainly, it has limitation, but it's capturing the physics, what is happening in the focal volume. So the rate of electron generation in time will be proportional to the electrons, free electrons you already have, and they are multiplied by avalanche rate, and atoms which are still not, and bonds, chemical bonds which are not ionized, they will be ionized by multiphoton ionization. So these rates can be easily calculated with a very small number of parameters, which are more or less known. So this is describing the thresholds very well, and this is describing light-matter interaction and those high-intensity conditions. So what we can create with tightly focused femtosecond pulse inside transparent dielectric depends how much energy we are absorbing. So have a look at this bottom line of energy per volume. So if we have a microjoule absorbed in 1 cubic micron, which is wavelengths of light, so it turns out by dimensions is actually pressure. 1 terapascal is the pressure ledger which we have in the center of our planet. So dynamically, you can create very huge pressures just by absorbing quite modest energy inside small volume. So high pressures is invitation to make new materials. It's also important that you can deliver the energy. You can heat up electrons and finally ions to very high temperatures in very short time. Fast cooling, which is another feature because modification is already localized in small micron scale, can be very fast. And this is another avenue which is favoring formation and capturing new material phases and recovering them to room conditions. If we look on this diagram of temperature and density, so you can see that so this star marked here, it's warm dense matter conditions. They can be created with the focus, which is around 1 micron in diameter, and absorbed energy around 200 nanojoules. Warm dense matter, it's a material which is described with the electron nuclear interactions, basically interaction in the atom, is comparable with the electron kinetic energy in the plasma at those intensities. So we can have very high density and very hot material, which is not very usual. So we can create in very unique conditions using femtosecond laser. So in very first experiments, we were using sapphire, which is the hardest oxide in nature. We had very thin film of sapphire, which is required for tomography measurements. And if you write a pattern of single shot illumination and you look at different angles, you can see that all those structures of modified volume is enclosed. It's slightly elongated because of spherical aberration, but it's really very, very well localized. If we see what is inside of those modified regions, you can, by simply breaking sample in half, you can see that it's pinched hole with a modified region around, and this cone is corresponding to the focusing cone of light. And this is each pulse is making single damage. And you see conditions. The energy of pulses, this is energy which is coming onto the sample. It's really quite small, but focusing is very tight. Once we know the energy which is absorbed in volume, we can calculate by equation of state how the pressure is evolving. So the pressure, temperature, and density evolution in time for absorbed energy, which is deposited in the volume, which we know this is spherical volume for the simulations was considered So this is in grayscale. In this volume, the energy of 100 nanojoules will drive pressures. You see the times. This is already, light is gone, so this is evolution of modification of material. There is formation of shock wave. Young modulus, this is dashed line. So you see that shock wave is well above Young modulus of material. This is why we can create strong modifications. If you look simulations for longer time, you can see that they're opening depression in density. This is void which we saw, and you have some shock wave which is with a small amplitude passing out of the focal region of modification. The radius of this opening is actually twice larger than we saw in experiments, but this is we consider it's good enough as first description. So you see the void in the center, you see around amorphous material, which is actually have density larger by the volume you expelled from the center. And this is not very usual to have amorphous state, which is more dense. Amorphous state can be washed out in acidic or basic solutions. And if you are capturing amorphous state, you can see it in electron transmission microscopy. This is the volume which is modified by single pulse. And just on the threshold when the opening of the void is happening, so if slightly larger energies are used, this would be the void, and all this volume is amorphized as seen by X-ray diffraction. This is electron diffraction. X-ray diffraction I will show later. So all these regions nearby, all perfectly crystalline. The rim can be very sharp, so you have amorphous and crystalline phase, which is just happening in nanometer scale. To characterize what is in that modified volume, you need simply more material. We wrote, we inscribed larger volumes of modified sapphire, and experiments were carried out in argon, which showed that the pattern, which X-ray diffraction pattern, has very, very symmetric structure, which was surprising because we were expecting something out of compressed sapphire, and this would be those magenta type of pattern, the peaks shown here, and nothing similar was observed in experiment. It was a very symmetric pattern, which was a hint that we have a very simple structure. And it turns out that we have body-centered cubic aluminum. It was predicted that it can exist at very, very high pressures, and it was demonstrated experimentally in this way of actually modifying sapphire rather than starting with the aluminum. Aluminum around us, it's always FCC. And in this experiment, we see that this is a different phase. So cartoon version of explanation how it happens. We start with the explosion, which is strongly localized, where aluminum and oxygen atoms and ions, they are ionized several times. They are departing in this very fast dynamic explosion driven by pressure, and separation happens because simply of difference of mass. And once it's quenched in some that modified volume, you will see BCC structure formed. Nanocrystallites are around 20 nanometer in size. Some oxygen should be present nearby. It can form new phases in sapphire, but it was not seen in this experiment. But I will show in next slide where we detect oxygen inside the volumes which we modify. So we took glass, which has a larger ratio between masses of elements. So germanium and oxygen has a bigger mass ratio if you compare aluminum and oxygen in sapphire. So here it's not a complicated experiment using synchrotrons. This is simply fabricating voids in glass and looking for Raman scattering. You can recognize the modification of glass. It's all understandable from glass science. But if you look for the place where you expect oxygen, you see that you can detect oxygen, and depending on how much energy was in your femtosecond writing pulse, you will see different concentrations. So oxygen is actually inside void, which you create with femtosecond pulse. So it was hard materials, oxides, but it's also valid, the same logic is valid for crystals, for example, biocrystals. Silk is a crystalline material. You see it here by diffraction pattern. It shows crystalline features. And single pulse is creating, obviously, ablation spot, but this material around can be washed out in water. And this is unusual because silk, if you modify it by temperature, it's usually polycrystalline, and silk is not easy to wash. So you need amorphous, which is quenched very, very fast to be able to have it water soluble. So it's another example of very fast quenching and capturing unusual state of material in the laser illuminated spot. Okay, so next we always asked about applications. So one application could be that we use modification of hard material glasses and crystals. In this case, for example, sapphire. You pattern by single shots some microfluidic channel inside and subsurface region of sapphire, and then you can etch out it in acidic solution, then fill with the dye for inspection. So you see the formation of 3D structures inside. So the same can be done in glass. And this is another example from colleagues' lab. If Beloard is cutting glass using femtosecond laser and etching, so he is interested in mechanical properties of those glasses. You can see that etching removed all the stress, which is all cracks are removed by etching, and this allows you to reach almost the limit for silica glass in terms of stress. It can withstand 2 gigapascal stress without breaking. So this is another example, which is now, if you want commercial 3D printing inside glass, you can send your file to the company in Germany, and they will print microfluidic channels for you, or they can make some more complicated 3D structures. This is demonstration of this reindeer has actually movable legs because it's very high precision of defining and etching out parts out of silica glass usually and sapphire. So 3D printing from those materials, now it's already established method. Okay, so now let's go to more recent things where we are using fabrication of micro-optical elements, in this case in sapphire. One thing which is added here is high temperature annealing after you ablate your 3D surfaces. And ablation also here is done in a slightly different way. You are focusing femtosecond pulse on the backside of transparent material, and this way is allowing to avoid any debris formation and flying into your incoming laser pulses. So it's removed from interface by cavitation, and this is the way how you can sculpture nicely 3D surfaces and optical elements. But all ablation is never perfect in terms of optical performance. It has some roughness, and you need to deal with it. For glasses, it would be high temperature annealing, which will make all surfaces spherical. And this is all not ideal. Sometimes we want surfaces which are not spherical, for example, a spherical lens. And here, with the crystal, is something different. Once we fabricate, we can actually apply high temperature annealing, and temperature is really high, but it is not high enough to melt sapphire. Sapphire is melting still 500 centigrades at high temperatures. So what happens that you can, after fabrication, this annealing is making very smooth surfaces. Here it's optical vortex generation, and here is diffractive optical element, which is defined by 4 levels to cover 2 pi phase, and all steps are ablated, and then after high temperature annealing, they are not disappearing. They actually are made much cleaner and much more defined. And you can also recognize that surface reconstructed by this high temperature annealing into a crystalline surface. You can recognize C-plane on surface of sapphire, which was used to ablate those diffraction optical elements. So certainly they will have some scattering because of the crystalline nature, but they don't suffer from the problems of debris, which is very usual for laser ablation. Okay, so next application is large surface area fabrication, and large area is a good example is solar cell. So can we really dream about writing patterns on surfaces of solar cells? Here we used silicon, we coated with chromium, thin film of chromium. It also can be dielectric. And we were writing single pulse ablation, driving at 10 centimeter per second. It could be faster. And at this rate, it was all perfectly aligned ablation patterns. And those, after you write mask, you put your sample into wet or dry etching, into plasma. Plasma is much faster. In minutes, you can make all the surface into well-aligned photonic crystal. Fabrication, writing the mask is begins to be 1 centimeter. It's very similar to electron beam lithography. Centimeter squares on an industrial scale tools takes some hours to modify. So photonic crystals can be made on large areas. For us, it's still large areas centimeters, but it's something very different, and we were not dreaming about this a few years ago. Currently, we made those patterns on the surfaces of solar cells. They are solar cells with all electrodes incorporated in the back. So we wrote the photonic crystal patterns on the front side, just above of that electrode shown here in this image. And with this type of light trapping, there is probability that you can reach the limit of light trapping by solar cells and reaching 30% efficiency on silicon. So currently, world record is around 27, but you need photonic crystal trapping rather than ray trapping to reach the limit which is allowed by thermodynamics, around 31%. Okay, and very final thing is to show that we can use femtosecond laser, tightly focused, almost in a way of electron beam lithography application. So here you see the titanium film, 10 nanometers. Let's consider its resist, and it's sitting on some transparent samples, let's say silica glass. Then if we have a nanogroove and we are focusing femtosecond laser on this type of structure, focus is larger, obviously, but if we have very narrow groove, what happens is that light will be very happily concentrated in the air part of this illuminated region. And why it is happening? Because it's just requirement for normal component of displacement to be continuous at the interface. So permittivity multiplied by electrical field in air should be the same as permittivity of sapphire, in this case, not sapphire or titania, and electrical field in the film. Intensity is electrical field square, so the ratio of permittivities squared will be a difference of a ratio of refractive indices to the power of 4. So the difference of light concentration here can be actually 20, 40 times. So then, by single pulse ablation, you create usually hole, what I showed before with the writing mask for photonic crystals trapping. There can be subdiffraction limit, but they are still large. They are hundreds of nanometers. But if you are very patient and your laser is stable, there is no any problem to ablate what is shown here, this hole, which is becomes your nanopen. You make single or double pulse ablation of a very small feature, then you reduce your pulse energy and you just drive the writing on the surface. There is also a possibility to steer the direction where you write. So if you change polarization orientation, you actually steer the tip of the intensity distribution into the direction you want. And this way you can, by changing polarization, you can turn very sharp corners and writing ablation groove, which is really on the scale of tens of nanometers. And you can write those nanogrooves very closely. So this is on the left side. This is really unusual. If you even consider electron beam lithography, it will be very challenging without any change of conditions to write patterns in close proximity without changing exposure dose. And here it's just comes for granted. You can write and modify nanogrooves on the surface of titania, your resist in this case, just without any complication. So let's look at this picture. So this is your diameter of focal spot. At first you ablate nano feature, and then you write using this nanostructure. Optical modeling of light field enhancement for such structures is shown here on the right side. What we have here is our titania film with the grooves. Two grooves are horizontal, one is vertical, and we have nanodots. So let's have a look what happens to enhancement of electrical field for different polarizations. For horizontal, you don't see those horizontal grooves, but you see very nicely that light is localized inside groove, which is vertical. If you have 45 degree, you have slightly smaller concentration of light in that vertical groove, but also you begin to see those horizontal ones. If you see that the dot, light is also concentrated inside, but you see some depression of intensity nearby. And this is the reason why you can write very closely nanostructures. Let's look at this vertical polarization, 90 degrees. So you see light is very happy inside the groove. It's high intensity, but this nano feature here has some light localization, but also has depression nearby. So this is, if you use this spot to write your modification of the surface, you can write very closely to something already exists and fabricated, and you will not damage it. So this is a really unique way of modifying surfaces, writing on dielectric films in a way as we are working with electron beam lithography and resist polymeric resist. So and also one important feature is that this type of writing can be also done on curved surfaces because there is no any limitation. And this is done simply by focusing your femtosecond laser and very good control of positioning. That's it. So this brings me to conclusions. I showed different applications. The key point is that now we can really think about large area applications. So centimeter square areas for photonic crystal light trapping becomes a reality. So direct femtosecond laser writing is useful because it has no requirements to have vacuum. Area is scalable. You can scan over large areas, and you can benefit from this very simple approach. Another feature which I just showed what is happening with femtosecond lasers. The average power is increasing. So our photons become less expensive, and we have more than need to write large areas. This is more material science conclusion that we can use ultra short pulses to create new materials because we can create very unique pressure temperature conditions, and we can retrieve new phases. So we can sculpture 3D structures for photonic applications, lenses, diffractive optical elements with a very precise definition of modification. And finally, which was a more recent development, that you can use nanoscale precision and lithography just by ablating nanofilms. With this, I also need to acknowledge all the teams which were contributing to different parts of results I shared with you. So on high intensity light matter interaction, we collaborate with the group in Bordeaux, with Vladimir and Eugene in Canberra, and Andrei Rodez. This is our team in Swinburne, current and past students. Thomas is helping with our nanotechnology facility applications. Some experiments which I showed about characterization of high intensity phases were done in collaboration with Arturas. Sajeev John is driving our designs for photonic crystals in photonic in solar cell applications, which is also collaboration with Nishijima in Japan. And the team in Jilin from Hong Bos Lab is behind that clever use of high temperature and making crystalline sapphire used for diffractive optical elements. Thank you for your attention.
Okay, thank you very much, Professor Saulius, for the wonderful presentation. So I hope the techniques you have developed will also benefit the field of holography for creating advanced holographic technologies. Okay, so now let us see if there are any questions from the audience. Okay, so any questions? Anything in the chat window? Okay, so there is a question from Daniel. So yeah, Daniel, please.
Hi, yes, I did have a question. When you talked about the nano writing of I think with the with the laser pen, I believe it was, and you were saying how close you could get together. I was actually wondering what is the limit that you can get the pulses together, the width together. At what point can you not go any closer? Yes, the nano pen. Yeah, so you talk about the width of that coming in. Yeah. So what's the limit?
Yeah, this will be defined. In this case, we used 20 nanometer film, so it was opening of 20 nanometer wide grooves in 20 nanometer thick film. So this, if film is thinner, you can very nicely open smaller groove. So this is basically also defined with the film you are depositing on the surface, and certainly precision of that first opening of your ablated hole in 1 or 2 pulses, because this is your writing pen. So once you have it smaller, you can reduce pulse energy in such a way that you are not modifying anything else, and only modification happens because of light concentration in that groove. So it's let's say short answer would be that it's mostly defined by thickness of your resist. If you want a smaller groove, and if you want to write them more close, your resist should be thinner.
Okay. Thank you very much.
Okay, so are there any other questions? So we have time for a few more questions. Anyone from the audience? Anything in the chat window? Okay, so if there are no further questions, let us thank the keynote speaker again for his valuable time and wonderful presentation. Thank you very much, Professor Saulius.
Thank you very much.